Good afternoon, ladies and gentlemen. My name is David Banda, the A Plus Ambassador, or you can call me the Investor Data Boy. Today, I'll be going over a requested question that came from a guy from one of his universities, must be CBU or UNZA. So, it's on rotational motion, and I'll flash it on the screen. You'll be able to see it. So, let me read the question. A student stands at the edge of a circular platform that rotates on a horizontal plane about a frictionless vertical axle. The platform has a mass m of 100 kilograms and the radius r of 200 meters. The student, whose mass is m equal to 25 kg, walks slowly from the rim of the disk toward the center. If the angular speed of the system is 2 rads per second when the student is at the rim, calculate A, the angular speed when the student reaches a point 0.5 meters from the center, and B, find the change in the system's rotational kinetic energy caused by her movement to the radius 0.5. As you can see, this question actually has a lot of marks, so definitely, and it's from a past paper actually, and definitely from here we know that it actually has a lot of work. So what we'll do here is we're going to apply the principle of conservation of angular momentum, which is angular momentum is conserved, meaning the angular momentum initial is equal to the final angular momentum when no torque is applied to the system. Torque is like the force in terms of rotational motion. So now trying to visualize what this is we have a disk and we have our student here. She's a girl, so she's standing here, then she moves. So now she's standing here, it's two, this is the center. Could have drawn a bigger circle. So she's standing here, it's 2 meters, then she moves to a distance somewhere there, that is, let's say, okay, let me use the same line, somewhere there, with this is 0.5 meters. So now this thing is spinning, they are spinning together. This is the system, it's the system of the student and the rotating disk. So now she moves from there to there, and we're told to calculate the angular speed. So we can equate the angular momentum that was here to the angular momentum that was there. So now angular momentum by L, angular momentum final is equal to angular momentum initial. And then first of all, sorry, we were supposed to do this in the first place. Let's organize our data. So I'm being told that the mass, the big mass, is equal to 10 kg. That's the mass of the disk. And then the radius is 2.0 meters. And then for the small one, the mass is 50 kg, and the radius for the small one, initially it was at the edge, so it was there, and then finally it's at 0.5 according to so r final, you can say 0.5 meters according to the question. And then the initial r is that one, so you can say r initial is equal to 2.0 meters because it was at the edge, so she was there, so that was the radius. And then what else? His mass has been written. And then the speed, the angular speed is 2 rads per second. Yeah, so now we are free to go into our question. So we have to know these formulas. The linear momentum L is equal to the inertia times the angular speed, which we've been given there, and then the inertia is equal to of a person or an object like a person is equal to m r squared. So this is the one of the student. I'll put it as is. Then the inertia of a disk, we can put it d is equal to the big M r squared, but there's a half 1/2. So that's the difference between these two, and you have to watch out for it as you are doing the question. So now we are saying that this one is equal to this one. So now initially we have this one, initial inertia, and then also initial angular velocity is equal to final initial times final angular velocity. So now this inertia is of the system, and the system is composed of two things. So to find the inertia, we must add them both, but then they are running at the same angular velocity. So the initial inertia will be this inertia, m r squared initial plus 1/2 r squared initial also. All this being multiplied by the angular velocity. And remember, we are looking for the angular speed when the student reaches this point. So we are looking at the final angular speed, and then we have the initial one, which is there. Always remember your known and your unknown values. So we have m. Now we go to this one, m r final squared plus 1/2 m r capital R final squared times the velocity. So now we can make this one the subject of a formula by multiplying both sides by, let me just write this, mr I squared plus 1/2 mri squared. Wi is equal to mr final squared plus 1/2 r final squared. So we can actually make this one the subject of the formula by multiplying both sides by, others will say dividing by this, but then in the actual sense we know that we are multiplying with the inverse of this. We are multiplying with m r squared f plus 1/2 m r squared, then this will cancel. Then we're doing the same this side, 1/r squared plus 1/2 capital M r, and then remember these are the final figures, the final. Then here they will not actually cancel, but then we'll be having these will cancel. It's like dividing these both sides. You can do it to simplify your work, but scientifically this is what happens. So now here we are going to have only this figure because this will cancel with that. So we're going to have w f where this squared come from, f squared is equal to this side we're having mri squared plus 1/2 capital, this is small r, yeah, it's supposed to be small r, this is small r capital M I, and then we're having this also r squared plus 1/2 capital M r. Fine. So this is the symbolic answer, and then when we plug in the values which we have there, we are going to find this. And then also, if you want to simplify your work, if you don't want to go through all this, you can just say, you can come from here, then you can make this one subject to a formula. So we have I, then when you make this one subject to formula, you're going to have W F by dividing both sides by F IF. We're going to have this one will cancel, then you're going to have your W final being equal to the initial and then the speed initial over the inertia final. Then when we plug in these values, you plug in the final inertia will be equal to this one, then the initial inertia, the initial inertia will be equal to this one, and the final inertia will be equal to this one. Then you still come back to this. So now let's plug in our values. We are having this being equal to our small m there, it's 50, and then r squared, our r initial is 2, because initially this guy was there, and then we have plus 1 over 2 capital M 100, and then we have r being equal to 2. For the disk, the r doesn't change, the radius is still the same throughout. All of this is over the same. M is 250. Now the r final it changes because this guy comes from there to there, so now his radius is 0.5. So I have 0.5 squared plus 1 over 2. The big M still remains the same. And the radius. So now remember we are multiplying all this by Wi. So you can say Wi is equal to the initial velocity, which is the initial angular velocity, which is 2 rads, because this is what the system had before this guy came here. Now this guy has come here, we want to know how the system is moving. 2 rads. So now we can begin our multiplication. 50 times 2 to the power 2 plus, we can write this one as 0.5 to simplify our work. 0.5 times 100 times 2 to the power 2. And remember, this actually follows BODMAS, so you can write this entire figure there. 400. So we're having our 400 there. 400. Then below we have 50 by 0.5 squared plus 0.5 times 100 times 2 to the power 2. So this is 212.5. So now we get 400 divided with 212.5 times 2. We are going to have the final angular velocity being equal to 3.76 rads per second. And that's all for this problem. And remember, you can actually do it anyway, but then use the principles that I've told you, meaning you can find this one first, you can find this one first, you can find this one, then you plug in the values, you're going to still find the same answer. And then we go to the second one, find the change in the system's rotational kinetic energy caused by the movement of the girl from the radius that she was at to a radius of 0.5. So now this girl moves from here to here. So now we have to know the change in the kinetic energy. How do we find that? We are going to find the final kinetic energy and subtract it from the initial kinetic energy. So you can get another paper. So for this one, we are going to we are saying we have the change in kinetic energy being equal to the kinetic energy final minus Ke minus the kinetic energy initial. Then remember, the formula for the kinetic energy for rotational motion is 1/2. It's just like the one for the normal kinetic energy. Kinetic energy is equal to 1/2 mv squared. But then remember, for rotational motion, the mass is like the inertia. The inertia is used like the mass, so you can put the inertia here. Then the velocity in rotational motion is the angular velocity. Then you put it to the power 2, so that's that for our equation. So now we can start by finding the kinetic energy final. You can start with initial, you can start with final, you can plug in them together and find your answers to find the same thing. As long as you do the correct physics, it's all about the physics. So we have our inertia final, angular speed final. Now the inertia, remember the formula for the inertia that I gave you? It's this one. So now this is for the system. So we have that of the small, you have that of this girl, and then that of the system. So we are going to add the two, 1/2, but then their angular speed is the same. Remember, the angular speed is the same. So now the inertia will be equal to the same one which was here, the same one which was here. I think let me just write it down. The inertia, oh, it's there. Yeah, it's there, the inertia. So you can just get it from there. So now the inertia is for the first one. For this one, the inertia is the small mass, the radius squared. Now remember, these are final figures, eh? Then we are going to add it to 1/2 the big guy, big M squared. Then we're going to multiply it by the angular velocity, the final. But then, do we have the final angular velocity there? No, we don't. But then we actually found it in our previous answer. So then we can get we can plug in the values. The small m, our small m is 50. Our small r is the final is 0.5 because it has moved now, 1/2. Then our big M is 100 kilograms. Our big R is 2. And then always get the stuff from your data. That's why it's important to always write down your data so that you don't get confused along the way. Then our angular velocity rather is 3.76. So we have about 3.76, the final one. So most physics problems are like this. So you have to find the correct figure here. If it's not correct there, then it will be wrong there. They are usually interlinked. So now we can start finding the figures. We can start so we start with 50 by 0.5 squared plus 0.5, the 1/2, times 100 times 2 to the power 2. We get that, and then we are multiplying this by 376 to the power 2. Then we are dividing it by 2. So I divide it by 2. We have to start again now. Be careful in your calculations. When you make a mistake, you just have to go back. Just have to go back. Yeah, that's that. So times 3.76 squared, and then we are going to divide this by 2. Sorry. So we're going to find our answer being 1,502.12. I think we can write that down. Then energy is in joules. We all know that energy is in joules. If you're a physics student, you surely know this. So then we go to the kinetic energy. initial, it's equal to it's equal to the same thing, except the figures are initial. So we have 1 over 2 initial inertia, initial angular frequency, initial angular acceleration rather, sorry. Yeah, so we go to that, we have 1 over 2. So we have the same thing, m r I squared plus 1 over 2 m big R. This was final, this one is initial squared, and then we have our angular speed initial. So we have our ke being equal to 1 over 2. It's just the same figures in here, except for this one, the initial, this guy was at 2, then he went to 0.59, so that's why his radius has changed. But then for the circle, it's still 2 meters. The circle is still 2 meters. Wherever this guy will be, he can go there, he can go there, he can go there, the circle will still actually have the same radius. So we have our that times 2 to the power 2 plus 1 over 2. The big M is 100. The big guy doesn't change, the power 2. Then this one, the initial, the one that it had before the guy actually moved, was 2 rads. 2 rads to the power 2. So now our kinetic energy initial is equal to, when you do the calculations, we start 50 times 2 to the power 2 plus 0.5, the half, times 100 times 2 to the power 2, that's 400. And then we're going to multiply the 400 by 2 to the power 2, this 2 to the power 2. Then we're going to divide this one by 2. Then we find our answer being 800 joules. So now this is the initial one. We can plug this in there, and then we can find our values. So now our kinetic energy final, our change in kinetic energy is equal to, the kinetic energy final is 1502.12 minus our kinetic energy initial is 800 joules there too. So our kinetic energy is now equal to, when you subtract that, it will be probably 700, and these figures that are there, but then we can do it for the sake of doing it. 0.112 minus 800, yeah, 702.12. So that's that for our question. If you have any other questions, you can send the questions in picture form to 0978957975. And remember, no calls, just WhatsApp. You WhatsApp the question to this number, then it can actually be solved. Physics is easy. Continue studying, guys. That's it for me. Remember to subscribe and share to people who you know would actually benefit from this. Thank you for watching. Have a blessed day.